drawing disdain from both die-hard manual enthusiasts and casual drivers alike. Yet, is this widespread criticism truly justified? Or should we take a deeper look at the CVT and perhaps even a bit of respect? CVTs were initially associated with low-cost, low-power compact cars due to their focus on fuel efficiency rather than performance. However, in recent years, advancements in CVT technology have enabled their integration into a broader range of vehicles, including high-performance, full-size sedans and SUVs. Despite initial skepticism and criticism, CVT transmissions have established themselves as a viable option for various types of vehicles. Even sport compacts like the Subaru WRX utilize continuously variable transmissions in place of traditional automatics. Additionally, the increasing popularity of hybrid vehicles has led to the development of the eCVT, a type of transmission that integrates both electric and gas drivetrains into a single output shaft, offering endlessly variable gear ratios. This widespread adoption indicates that CVT technology is here to stay, as automakers continue to invest in its development and integration into their product lineups. So in this video, we are taking a look at these different types of CVT transmission used in automotive industries. To understand the reasons behind the dislike for CVTs, we must understand how they're different from a traditional automatic transmission. In a standard automatic, gear changes are typically facilitated by hydraulic pressure, acting on various gears ratios, allowing for seamless acceleration without discrete gear shifts. Most CVTs only have three basic components: a high-power metal or rubber belt, a variable input driving pulley, and an output-driven pulley. CVTs also have various microprocessors and sensors, but the three components are the key elements that enable the technology to work. Variable diameter pulleys are the key components of a CVT. Each pulley consists of two cones facing each other. A belt rides in the groove between the two cones of each pulley. This belt serves to transmit power between the input and output shafts of the transmission. V-belts are commonly used in CVTs, especially when the belt is made of rubber. The term V-belt refers to the V-shaped cross-section of the belt, which increases the frictional grip of the belt on the pulleys. This improved grip helps prevent slippage and ensures efficient power transfer. The first pulley, known as the input pulley or drive pulley, is typically connected to the engine's crankshaft. The second pulley, referred to as the output or driven pulley, is linked to the drive pulley through the belt and transfers power to the drive shaft or wheels of the vehicle. These cones are hydraulically controlled, allowing them to be pushed together or pulled apart from each other, depending on driving conditions. Instead of belt advantages over rubber belts, including increased durability, reduced slipping, and the ability to handle higher engine torque. Additionally, they tend to be quieter in operation compared to rubber belt-driven CVTs. In modern CVTs, both the input and output pulleys are typically made with cones to allow for a wider range of variability in gear ratios. This design enables the CVT to adapt to various driving conditions and deliver optimal performance across a broader spectrum of speed. At low speeds, the cones comprising the driven pulley are typically positioned as far apart as possible. This configuration allows the belt connecting the pulleys to rest at the narrowest diameter on the drive side of the pulley. As a result, the input shaft spins rapidly relative to the output shaft, which maximizes torque delivery to the wheels. This setup effectively mimics the characteristics of first gear in a conventional automatic transmission, creating a gear ratio optimized for strong low-end acceleration. As the vehicle accelerates, the input pulley cones of the CVT are gradually brought closer together, causing the tips of the cones to come into contact and pushing the belt upwards along the walls of the cones. This action effectively increases the effective diameter of the pulley. This results in the drive pulley spinning more slowly relative to the driven pulley, similar to the operation of an overdrive gear in a traditional transmission. This configuration allows for higher vehicle speeds at lower engine RPM, optimizing fuel efficiency and reducing engine wear during highway cruising. In order to achieve reverse gear in CVT, an interesting planetary gear set arrangement is used. The input shaft is connected to the sun gear of the planetary gear set. The sun gear is one of the three main components of a planetary gear set and typically rotates in the center. The carrier of the planetary gear set is fitted with the input pulley of the CVT. The carrier is another component of the planetary gear set and is positioned between the sun gear and the ring gear. This makes the planetary gear set work together to move the car forward smoothly. To go in reverse in a CVT transmission, simply shift the gear selector into the R position. The transmission engages a clutch to hold the ring gear still. This makes the planet gears and carrier rotate in the opposite direction, effectively reversing the direction of the output shaft. Milton Reeves invented a variable speed transmission, an early form of CVT in 1879 for use in sawmills. He later adapted this transmission for use in automobiles, starting in 1896. Several other manufacturers also utilized the Reeves CVT in their cars. In 1911, the Zenith Gradua 6 HP motorcycle was noted for using a pulley-based CVT. This was one of the early applications of CVT in motorcycles. The Rudge Whitworth multi-gear released in 1912 also featured a CVT, similar to the Zenith Gradua, but with improvements. This was another significant early application of CVT technology. The 1913 to 1923 David, a small three-wheeled cycle car built in Spain, the 1923 Clino from the UK, and the 1926 Constantinesco Salon, also from the UK, are all noted for using CVTs. These early cars demonstrated the early experimentation and application of CVT technology in the automotive industry. The earliest practical application of CVT-like technology, continuously variable ratios. Over time, the rubber belts could get stretched, affecting the performance of the transmission. However, the 22 horsepower 590cc air-cooled DAF engine was luckily low stress, which helped mitigate some of the issues associated with belt stretching. The 600 became a massive success in Europe thanks to its excellent fuel efficiency and compact size. These engines were even sold briefly in America in the 1960s. They were eventually banned from American roads due to a variomatic design flaw. Early DAFs had no park gear. They only had drive, neutral, and reverse gear. The US government deemed this unsafe and stopped sales. After DAF disappeared, Americans wouldn't get another CVT until the Subaru Justy in 1989. The CVT in the Justy was a more modernized version compared to early variomatic transmissions, with a traditional reverse gear and park function, addressing some of the safety concerns that led to the discontinuation of DAF vehicles. The introduction of computer-aided design and advancements in material science led to significant improvements in CVT technology. These advancements allowed modern CVTs to handle more power without significant belt degradation. By the early 2000s, several major manufacturers, including Honda, Nissan, Subaru, and Toyota, began incorporating CVTs into their vehicles. This marked a significant shift towards the widespread adoption of CVT technology in the automotive industry. The DCVT has additional gears and a planetary gear set fitted to the input and output shafts of the pulleys, with a clutch pack to engage or disengage. In normal operation, when you're pulling off from a stop and traveling up to low to medium speeds, the DCVT functions like any other CVT, the power from the end of the belt drive. This gear drive provides a more efficient means of power transmission, particularly at higher speeds where the belt drive may become less efficient. Compared to a regular CVT, the DCVT in split mode experiences fewer energy losses as the friction that comes with the belt drive in play is removed. This results in improved transmission efficiency by 12% at 60 km per hour and by 19% at 100 km per hour. In traditional CVTs, there might be a delay or sluggishness in acceleration from a standstill due to the nature of how CVTs operate. To address this, Toyota has implemented a launch gear in some of its CVT-equipped vehicles. While both the DCVT and direct shift CVT have additional gears in them, Toyota's approach is totally different as it adds on a launch gear that acts like a first gear in a conventional transmission. The launch gear is used when setting off from a stop, before the transmission switches to a belt drive like a CVT instead. This launch gear is essentially a fixed ratio gear that aims to provide a more direct power delivery and improve the vehicle's responsiveness. The launch gear is engaged when the vehicle is at rest. It is used solely to help the vehicle accelerate up to speed more quickly and efficiently from a stop. Once the vehicle has reached a speed where the CVT transmission is more efficient, the launch gear is disengaged and the transmission functions like a CVT. Toyota's direct shift CVT was first revealed in 2018 and was designed to offer a more direct drive connection at low speeds. It is not the same as the older CVTs used in the Vios and Yaris, and not all models get it, even the newer Corolla Cross. The DCVT is like a flipped version of the direct shift CVT, as gear drive is used at higher speeds rather than for setting off. So why not just adapt Toyota's technology in every DCVT? Well, adding a gear selector to engage the launch gear increases the complexity of the transmission, which could be costly and wouldn't be suitable for budget vehicles. eCVT is a different, more generic name for the hybrid powertrain installed in all pure Toyota hybrid vehicles. Toyota calls it, though it works based on an entirely different principle and avoids all of the disadvantages of a conventional CVT. In a hybrid vehicle, the eCVT can be powered by different sources to the wheels. When the vehicle runs solely on battery power, it is in a pure EV mode. When both the battery and engine work together, it is a hybrid mode. When the engine takes over, typically when the battery is empty, it is in engine mode. The toroidal CVT is another version of the CVT. It is slightly different from a pulley-based CVT. The design contains a pair of discs and rollers, instead of belts and pulleys. Two rollers in the middle of two discs manage torque distribution to enable an infinite number of gear ratios. One disc is the input, which connects to the engine. This is equivalent to the driving pulley. The other is the output that connects to the drive shaft. This is equivalent to the driven pulley. Between the discs are rollers act like the belt, transmitting power from one disc to the other. In this system, power is transferred between discs using rollers. When the rollers align perpendicularly to the discs, the effective diameter is the same for the input discs and the output discs, resulting in a 1-to-1 drive ratio. But by rotating them along the discs, different ratios are achieved. An advantage of a toroidal CVT is the ability to withstand higher torque loads than a pulley-based CVT. In some toroidal systems, the direction of thrust can be reversed within the CVT, removing the need for an external device to provide a reverse gear. These rollers can tilt, touching the discs at different points. When they touch near the center of the driving disc and the rim of the driven disc,